Good day, I'm Dr. T and welcome to my office. So as chemists, we sometimes get into this interesting situation where we look at the world and we try and figure out what's going on and we create a model of that topic, a way of thinking about it. But only to realize that that model's incomplete, so we build a new model and possibly even another newer model after that. But we look back and go, you know, those early models, they weren't complete, they weren't perfect, but they were useful. I mean, they were simpler, they were easier to use. Now, let's not throw them out. Let's just keep them around and, you know, we'll know when we have to use the more complicated ones. And that's kind of a weird way to think about things. Of like, well, this isn't perfect, but it's good enough. And acids and bases are going to be a case study in this weird keeping a model even though we know it's highly imperfect. So let's go back to the 18th and 19th century. At this time, we are looking at all kinds of chemicals, and we're starting to realize there's a couple of types of chemicals that have an interesting relationship, and they're definitely very important. There's those chemicals that we're going to call acids and those that we call bases, and they almost have like this opposing relationship. So if you were to taste one, and acids, they typically are going to taste sour. Bases will be bitter. But if you mix them together, then the sourness and the bitterness goes away. That's why if you say cook spinach and you add some vinegar or lemon juice or tomatoes, then that bitter spinach flavor that most people don't particularly care for goes away. And now all of a sudden it tastes pretty tasty. Pro tip, cook your spinach with some acid. So then the question goes, okay, this is interesting. They have this like neutralization relationship. The acids can neutralize bases and vice versa. We also looked at them a little bit further. They will change the color of certain dyes. Dyes that they can change the color of are going to be called indicators. So litmus is one of the most famous. It was an early one. Actually, some of the first ones were violets. But litmus is a classic one. Acid on litmus goes red. Base on litmus goes blue. Acid will turn blue, litmus red. You can fight them back and forth, and if you mix them in the right ratios, they cancel each other out. Bases will typically feel slippery. Acids, not quite so much of a feeling to them, other than, you know, you can start getting a burning sensation, but you can get that from bases also. At high enough amounts, both of them will hurt you. So the question is, well, what is up with these acids? What makes an acid and a base a base? And first we come up with this idea called an Arrhenius acid and an Arrhenius base. You'll never guess the name of the person who came up with that one. Yeah, we like to name stuff after people, so it would be Arrhenius. And in this definition, acids are basically going to be like ionic compounds, although, spoilers, they're usually not ionic compounds, go figure. But they're ones that are going to have hydrogen effectively as a cation. So acids are going to give up H+. They're going to be something that can give away an H+. Now, that H+ doesn't float free by itself. It always piggybacks on something like a water molecule. Now, with the base, when looking at those, it was thought, like, okay, so a base is going to be something that has a hydroxide, an OH, as its anion. So now the OH separates. H plus OH gives you HOH, which would be a lot like H2O. It's water. So when an Arrhenius acid means Arrhenius base, then the anion from the acid and the cation from the base will join and make a salt, and then the hydrogen and hydroxide turn into water. And this is a great definition, and all works well, except for the fact that there are bases that don't have oxygen in them, like, at all. The one that we normally run into is ammonia. Ammonia is NH3. Okay, how is this a base? It's definitely a base. Well, then comes in our new model, the Bronsted-Lowry model. So Bronsted-Lowry acids and Arrhenius acids are basically the same thing. You can usually tell that these guys are going to be an acid because they have an H right up the front, right in the cation position, even though quite often it's actually a covalent compound, and therefore, you know, it's not actually a cation. There are a couple of organic acids where the H will actually live on the back end. Once you start dealing with carbons, the rules change. It's actually a completely different set of rules on how to write the formulas, because of course it is. Okay, so we basically have the same idea, whereas the bases, and really looking at the acids on this one, an acid is something that makes more H plus in solution. So it's probably just going to hand it over, probably just give up the H plus, but in reality it just needs to make more H plus. So we could go around a little bit more of a circuitous route to increase the amount of H plus in solution, and the base is going to be something that increases the amount of OH minus in the solution. Whether or not it gives it away, that's a different story. So anything that just simply go here, have an OH minus, okay, that's Bronsted-Lowry base as well as an Arrhenius base. But ammonia is one was like, oh, hey, water molecule, why don't I take one of your H pluses? I'm now going to suck up an H plus, and in doing so, that's going to allow me to increase the amount of OH minus in an aqueous solution. A Bronsted-Lowry base, these are going to suck up H plus, thereby increasing the amount of OH minus. Okay, this makes sense. But then we ran into things that don't even do that. And what if water is not involved? So the last one that I'm not going to go very far into is the Lewis acid and Lewis base. In this case, a Lewis acid is anything that will react with a lone pair. So if I have, say, an H plus, those will interact with a lone pair and form a covalent bond from that lone pair. Now, if I have a base, a Lewis base is anything with a lone pair that's willing to go react with somebody who would like to. And thus, say the OH minus, it's got 3 lone pairs, all of which, hey, we can hop a hydrogen on here. And thus, this guy is a base by all the definitions. Okay, so yeah, 3 different models. Most of the time, Arrhenius acid and base is really the model we want to go with. The only major chemical that you run into on a daily basis that doesn't fit as Arrhenius acid or base that is an acid or a base is going to be ammonia, which is a Bronsted-Lowry base. But Lewis acids and bases are there for a reason, and there are definitely compounds that you interact with that are acids and bases, but they don't meet either of the other 2 definitions. And I should point out while I'm talking about acids or bases, you can also be amphipathic. Probably just butchered that word. I'll spell it over here. In which case, you are both an acid and a base at the same time. So a classic case would be that of bicarbonate. Bicarbonate is a polyatomic anion. It's a carbonate, so carbon and 3 oxygens, but one of those oxygens has attached to it a hydrogen atom. Now that hydrogen atom could dissociate, thereby making that an acid. Alternatively, one of the other oxygens could accept a hydrogen cation, forming a covalent bond, thereby making it a base. Thus, it can easily be both. So with that said, have a wonderful day, and I will see you in later videos.